Hello and welcome friend. In this video we discuss about the complementary functions where the root of auxiliary equations are equal and imaginary. The nth order differential equation is dny by dx raised to n plus p1 dn minus y by dx raised to n minus 1 plus p2 dn minus 2 y by dx raised to n minus 2 plus pny equal to 0. When we put y equal to e raised to mx, then we get m raised to n plus p1 m raised to n minus 1 plus p2 m raised to n minus 2 plus pn equal to 0. This is an auxiliary equation. When this auxiliary equation have m1, m2, mn are roots and these are the different roots, then the solution is y equal to c1 e raised to m1x plus c2 e raised to m2x plus cn e raised to mnx. Now what happen if the roots are equal? That means if m1 equal to m2, then we get y equal to c1 e raised to m1x plus c2 e raised to m1x plus cn e raised to mnx equal to c1 plus c2 e raised to m1x plus c3 e raised to m3x plus cn e raised to mnx. Now instead of this c1 plus c2, we can write another constant, but then the number of constants becomes less than the number of order of the differential equation, and hence we have to proceed in another way. Suppose we consider that m2 equal to m1 plus h, where this h tends to 0, this m2 tends to m1. Now consider this case, c1 equal to y equal to c1 e raised to m1x plus c2 into e raised to m2x, that is m1 plus h into x, this much part of the above solution, this solution. Now you can see that we can write it as c1 e raised to m1x plus c2 e raised to m1x into e raised to h into x, taking e raised to m1x common, equal to e raised to m1x into c1 plus c2 into e raised to hx. We know that what is the exponential expansion of this function. We can write it as e raised to m1x into c1 plus c2 into 1 plus hx plus h square x square divided by 2 factorial plus infinite term. Then you can see that this is e raised to m1x into c1 plus c2 plus c2 hx plus c2 into c2 into h square x square divided by 2 factorial plus the infinite term. Now friend, here we replace this c1 plus c2 by a and c2 into h by b. That means if we take a equal to c1 plus c2, another constant, and b equal to c2 into h. Likewise, suppose for example this c2 is equal to 5 and here my h is equal to 3, then c2 3 5 into 3 is 15. So we get a new number, and for this new number I have denoted by this notation capital B, and for these two arbitrary constant I have taken new arbitrary constant, that is capital A, and we adjust this higher term in a such way that since as h tends to 0, we are adjusting this a and b in a such way that this a equal to c1 plus c2, this is constant, and b are finite. As h tends to 0, we adjust, we take this a and b in a such a way that as h tends to 0, a and b will be finite. So when a and b will be finite, we can write this term as y equal to e raised to m1x into a plus b into x. So look at this, when the roots are repeated, when the two roots are equal, we have the term e raised to m1x into a plus bx. Okay, so here you can see that when in this equation, in this solution, as the auxiliary equation has two repeated roots, then the solution of this equation is written as y equal to a plus b into x into e raised to m1x plus c3 e raised to m3x plus cn into e raised to mnx. Okay, and the number of constant now will be equal to the order of these differential equations. When three roots are equal, that means whenever m1 equal to m2 equal to m3, then the solution will be like this. We can write it as c1 plus c2x plus c3 x square into e raised to m1x plus cn into e raised to mnx. So this is about when the roots of the auxiliary equations are repeated. Now when the roots of these auxiliary equations are imaginary, this case arises when the roots of the auxiliary equations will be imaginary. Now you can see that, let us consider if we have two roots are imaginary, that means let us take particularly, suppose my m1 equal to alpha plus ib and m2 equal to alpha minus ib. These roots are imaginary roots. Then consider these roots, then solution for the first two roots will be like this: e raised to m1x means alpha plus ib into x plus c2 into e raised to alpha minus ib into x. Now here we write it as c1 into e raised to alpha x into e raised to I beta x plus c2 into e raised to alpha x into e raised to minus I beta x. Okay, now we know that e raised to I theta equal to cos theta plus I into sin theta, and e raised to minus I theta equal to cos theta minus I into sin theta. These are the Euler's formulas. So we put here the Euler's formulas: c raised to c1 into e raised to alpha x into, look at this, this is equal to cos of beta x plus I into sine of beta x plus C2 into e raised to alpha x into cos of beta x minus I into sine of beta x. Okay, now you can see that we can take e raised to alpha x common. If we take e raised to alpha x common, then here C1 and cos beta x, here C2 into cos beta x. So this is equal to C1 plus C2 into cos of beta x plus, now here I into C1 minus C2, here I common, C1 and minus C2 into sine of beta x. Okay, so this is equal to e raised to alpha x into, for this C1 plus C2, for this C1 plus C2 we can write another constant C1 plus C2. Instead of C1 plus C2 we write it as A, and this I into C1 minus C2 we write it as a B. So A into cos beta x plus B into sine beta x. So this is the solution when the roots of the auxiliary equations are imaginary. So remember these things when the roots are like this, m1 into I alpha into plus I beta and m2 equal to alpha into minus I beta, then these pair of imaginary roots, here e raised to this alpha is a real part, e raised to alpha is a real part into x, and these imaginary parts will become here in the here in the angle. So we can write this, and whenever the roots are again repeated, then we have y equal to e raised to alpha x into a plus a1 into x cos of beta x plus b in plus b1 x into sine of beta x. So this is the solution of the these equations. Now let us see examples. We will discuss about the examples. This is all about the theoretical parts of this imaginary roots and repeated roots. Now we consider, let us see examples of these repeated roots and imaginary roots. Let us suppose that my equation is d2y by dx square minus 6 into dy by dx plus 9y equal to 0. Then you can see that here how to write the auxiliary equations. Let us see the degree of this order of this differential equation. What is order? This order is 2. So write down m square minus constant as it is. Here you can see degree is 1. So write down here m raised to 1, m raised to 1 m plus 9 as it is. For this y we have m raised to 0, and m raised to 0 is equal to 1. Okay, so the auxiliary equations is equal to m square minus 6m plus 9 equal to 0. This is my auxiliary equation. Now friend, this is expansion of m minus 3 whole square equal to 0. Then here m is equal to 3, but this is a square term, so this is a repeated root and roots are equal. So very simple. Then solution of this differential equation is y equal to c1 plus c2 into x into e raised to m1x. What is m1? m1 is 3. So e raised to 3x. This is the solution of the differential equation. Now let us see the root like when example when where the roots are imaginary. D2y by dx square plus 4 into dy by dx plus 5y equal to 0. Now here again you can write the auxiliary equation. So look at the degree of this order of this differential equation, and write down the power indices of m as equal to order of the this differential coefficient. Then here is a 1, so we write it as a m square plus 4 into here is a 1, so we write it as a m square plus 5, here is a nothing, that means m raised to 0, and m raised to 0 is a 1. Okay, so sometimes what happen, you put this term as it is, and you will very trouble in finding the roots of the this auxiliary equations, how this m raised to 0, what to do with m raised to 0, and that is why do not write anything in here, and just write the constant term as it is, and you will get here. Then you can see we have a very simple, here is a 1. Okay, so my different auxiliary equation is m square plus 4m plus 5 is equal to 0. This is the auxiliary equation. You can see if we compare this ax square plus bx plus c, then we know that how to find the root of this is equal to minus b plus minus under root of b square minus 4ac divided by 2a. This is the standard formula. You can apply the to find the root of this formula. Then here you can see that a is equal to 1, b is equal to 4, and c is equal to 5. So if we put here these values, we get minus 4 plus or minus under root of b square 4 square minus 4 into a is 1 and c is 5. Okay, so divided by 2 into 1, then this is equal to here this m equal to minus 4 plus or minus under root of 16 minus 20 divided by 2 equal to minus 4 plus or minus, this is under root of minus 4 divided by 2 equal to minus 4 plus or minus under root of minus, for under root of minus we write I, and under root of 4 we write 2 divided by 2. So you can see minus 2 plus or minus I 2I, this is like this alpha plus or minus beta I. We have taken two terms, alpha plus beta I and alpha minus beta I. Then we have the solution. What is the solution of this alpha plus 2I? Y equal to e raised to alpha x a into cos of beta x plus b into sine of beta x. Then here you can see that this alpha equal to 2 and beta is also equal to 2. Therefore the solution of this equation equal to solution of this equation, we write the solution of this equation here. This is equal to, just write the values of alpha and beta. E raised to alpha means what, 2x plus into a into cos of, what is beta, beta is again 2x plus b into sine of 2x. So this is the solution of the differential equation where the roots are imaginary. Okay friends, thank you for watching and being with me. I hope you will get the idea of how to find the roots of the auxiliary equation and how to solve the differential equations where